Other questions? Yes, Eugenia.
Would you give an example beyond the paleoclimate data simulation of how, when you would use the offline approach?
Yeah, so the question, if you didn't hear in the back of the room, is can you give me another example of when this offline approach might be useful? So I had another student that was interested in assimilating pressure from smartphones and from other dense mesoscale networks of pressure measurements at the surface. Pressure is a really useful summary measure of the atmosphere that does not suffer from a lot of the same problems of sighting. So instrument sighting for wind and temperature and things like that can be sensitive. Barometers are pretty robust. We carry them around in our pocket now, so we can crowdsource these measurements. And we were curious about what impact they would have. So we have a local operational Ensemble Kalman filter running. So we have these samples. We say, okay, well, what would happen if we introduced these pressure measurements? And so rather than putting them in and cycling, we said, well, just as a start, let's just take all of our 6-hour priors and run the pressure measurements through them and see what kind of improvements we get, see what kind of analysis increments that we get. And then we don't have to worry about what they're doing to the wharf model when we're cycling, or the expense, or the weight. You essentially get the answer very, very fast. You're welcome. Other questions? Yes, sir.
Super observation that you were telling, is this some kind of overestimation? Overestimation?
You mean overfitting?
Yeah, actually underestimation and overestimation. There are two kinds of things.
Yeah, if I understand the question, I think the answer depends upon how accurately one has estimated the error variance of the measurements. And the prior, too. It really comes down to that ratio of those two things, whether the fit will be under or over. That's why it's so important to get a robust estimate of those two things. Yes, ma'am.
In that vein, how do you inform your estimate of the, say, the prior variance? Because I can understand how you would figure out what the measurement variance is, but if you don't know how accurate you are, how do you make that estimate?
Yeah, so let me deal with the assumption part of your question, which is, well, we know what it is for the measurements. It turns out we don't, and I think, as was discussed yesterday, there is the part that comes from the instrument itself, which is mostly irrelevant most of the time. The big piece is coming from other sources of uncertainty, like representativeness or the forward operator. And those are pretty big, and for the paleo problem, it's gigantic, as I'll show you. But getting to the real gist of your question, how do we get this for the prior? So that's coming from the model. So it comes down to how much do we trust our model. So if our model has a bias, it doesn't produce enough forecast error variance, we have a problem. I think a really common example with that for weather prediction is that we often have deterministic land surface models, deterministic sea surface temperature estimates. And so that gives us, even if we're running an ensemble, essentially fixed boundary conditions that reduce the amount of variance that we have in near surface fields. That means it's difficult to get a lot of information out of the surface-based measurements because we think we have a highly confident estimate about what the state is when we really don't. It's just that we've damped away all the variance. So it comes down to doing this and checking to see how well your background is calibrated. If it's really under-dispersive, then something must be done to deal with that. So I think even if you don't have a solution to the problem, knowing that the patient has a symptom, has a fever, is a good starting point. Any other questions?
I'm sorry, I don't understand the rotation in that equation, actually.
Sorry, I cribbed this out of my book. So M is the ensemble size. These angle brackets are expected values. Technically, they're expected values over an infinite number of realizations over the whole attractor for the system. M, again, is the ensemble size. And E is the error in the ensemble mean. And S is the variance in the ensemble. Technically, when we're doing data assimilation, this should be the innovation variance. It's the variance of the prior plus R. Good reference on this is Peter Houdekammer. I can tell you how to Google his name later, but he's got some good examples of how to do this. Any other questions? Okay. Oh, yes? Oh, sorry, I didn't see your hand.
I guess a question about the super observation.
Yeah.
For that portion, is it still assumed that everything is Gaussian? Or at least for that portion?
Yeah, pretty much everything I'm going to tell you today is assumed Gaussian. Yeah. Although I am going to generalize this idea that the measurements are identically distributed. I think the cool thing is going to be when we do the paleo problem, they're really heterogeneous, and there are ways of forming linear combinations of the measurements that's analogous to averaging that allow us to optimally map that information to the state. But I know that's very cryptic. That's one thing I hope to touch on this afternoon.
And I guess probably a quick question about that.
Yeah.
Does each one of those sort of data sources have to have or match up at the same point, kind of? Or?
So let me give you a concrete example. So when we've assimilated cloud track winds, so these are winds that are deduced from satellite imagery by monitoring cloud elements and tracking them in imagery and time. And so by the cloud drift, the cloud motion, we can get the winds from the infrared temperature of the cloud. We know their height. And we have a lot of these things, oftentimes within individual grid cells. So we would often super-ob them by averaging over them and getting a single representative measurement with smaller error that represents the net cloud track winds in the box at that level. Yeah.
So for super observations, I guess that ensemble size will be very much larger. That means M will be tending to infinity soon. Then expected value of EM will going to be expected value of S.
Well, we have two different things here. One is for the ensemble, and for the super-ob, it's whatever number of observations we happen to have, right? Which is independent of the size of the prior. All right. Yeah, so this is collaborative work with Robert Tardif at the University of Washington, Chris Snyder at NCAR. And again, we're trying to figure out how we can use the robust, long-time, dense measurements we have in the atmosphere to constrain the deep ocean on long time scales for decadal analysis and prediction. So, you know, the very first question is coupled data assimilation needed? There are some known alternatives, what some people call thinly coupled, where we do independent analyses. So if you're an ocean data assimilation person, maybe you'll do your ocean data assimilation. The atmospheric person will do the atmospheric one, and they share a common boundary condition, such as the sea surface temperature. Then there's what some people will call weakly coupled, where you run a fully coupled model, but then the data assimilation is performed independently in each medium, in the ocean and the atmosphere. And then in the stronger versions, we really want to use information from one side of the medium to update the other side of the medium. And in practice, it's really, can we use this atmospheric information to constrain the ocean in places that we didn't observe? All right, so the approach that I'm going to run through relatively quickly now is that we're going to try and do this with a simple coupled model that involves a Lorentz model of wave mean flow interaction for the atmosphere. So it's a very simple model of the jet stream with a single Rossby wave upon it, a weather wave, Henry. And so that's going to be coupled to a box model for the ocean. So this is a very, very simple representation of the ocean that can be used to model this overturning circulation in the simplest fashion possible. I can't, unfortunately, go through the details here. I don't have time. But we have some essential physics, not all of it, for variability in this overturning circulation. But basically, the things that drive buoyant-driven circulations overturning in the ocean involve temperature and salinity differences in the ocean, which can be related to the atmosphere in some nonlinear fashion through the water cycle, through the hydrologic cycle, through evaporation and precipitation. And this simple model has a cartoon of that. And it's low order and fast to run, so we can do lots of experiments. So we'll go straight to the problem of limited ocean observations. Let's say we'd like to initialize the ocean in the 1920s and predict the 1930s and 1940s. Again, something we've observed to test our decadal prediction system outside of the realm that we know about with robust measurements, which is really only the last 10 years. So this shows you on the ordinate a measure of this overturning circulation. And this is a simulation experiment where we know the true state. We sample it for measurements. The red line shows when we do assimilation every day in this model, if we measure pretty much everything we've got, we can track the system perfectly. If we only know information about the atmosphere and temperature in the upper ocean, we can kind of track the overturning circulation. If we only know about the atmosphere, we decouple. We can't constrain the overturning circulation. This is not a surprise. In traditional Kalman filtering, we're relying on, in this BH transpose, which can be rewritten as this covariance between YE is the estimate of the measurements, X is the state. So this covariance between the atmospheric measurements, which are fluctuating on fast time scales, with the ocean, which is evolving on slow time scales, is being contaminated by the fast noise in the atmosphere. There's no way we could take the day-to-day measurements and map them onto this slow, annually timescale situation. It's not average. It's not affecting the average state. But in fact, if we look at the correlation between these atmospheric variables in this model and the overturning circulation as a function of averaging time, we see there's no skill on short time scales, but once we get beyond a year, we suddenly have a very strong correlation. So again, this notion of averaging can boost signal to noise. If we start to average these atmospheric measurements, noisy as they are, back onto a time scale that's representative of the thing we're trying to reconstruct, there's a lot more information here that we can suddenly get onto. Same exact measurements, we're just treating them differently. And it matters which variable we pick, including linear and nonlinear combinations of those measurements can further boost signal to noise. And I can't go into that here, but that's the essential message. And this kind of reinforces the point. Each one of these bars shows you a different state element in this coupled model. The ones on the left are the atmospheric variables. The ones on the right are the ocean. And we're looking at the size of the ensemble one would need to capture the true correlation with 95% confidence. And so you can get it for these atmospheric variables, the wave on the jet stream and the fluctuations of the jet stream itself. If you had ensembles of size 50,000, 100,000, you could actually tap into that very, very weak covariability. But these are impractically large ensembles, right, even for a small model. But if we go to time averaging, the size of those ensembles collapses. We can now get access to that delicate signal with much more reasonably sized ensembles. And again, if we pick the right variables, E is one that couples through the hydrologic cycle, and it's a nonlinear function of the eddies. All of a sudden, that collapses from several thousand ensemble members down to about 10 when we get to annual timescales. So that's great. And we can now use this information in an effective way. I have 1 minute to go, so I can't give you the theory. The bottom line is, if your observation operator is a nonlinear function of time, you're screwed. If it's a linear function of time, you're good to go. You can look at the slides at your leisure afterward. Now, if we do this, we find that we track the atmosphere better, and even better still, if we pick the right variable. So now we're doing annually averaged atmospheric measurements for the eddy energy. The eddy energy is the thing that is driving the hydrologic cycle. These are the extratropical storms that are dropping precipitation like we experienced yesterday. And lo and behold, if we do yearly assimilation on those, they track the state. And in the real world, this is essentially getting the high latitude eddy heat and precipitation flux, which is driving the buoyancy into the ocean at high latitudes.
So is this a very approximate way of doing like a variation of bar over a year or something? A very simplistic?
It's even simpler than that. It is simply averaging, straight up averaging. So we're not cycling, we're not using an adjoint.
I mean, you're only adjusting the mean, essentially.
That's right. That's right. That was part of the theory that I just skipped over.
Yeah, I mean.
So you can partition the Kalman filter between this time mean and the deviations from the time mean. And the key comes down to this covariance between the mean state and the estimated observations on a time scale. And that covariance becomes much more robust when you go to these average time scales. That's where the dynamics live that we're trying to constrain. The observations didn't originate there, but we can take them there with this simple averaging operator. We could also update the deviates from the mean state at all times we might wish, and that involves a covariance between these high-frequency timescales and their measurement, and that covariance is a thing that's all noise, right? That's essentially 0. So we don't even bother with this. You could if you wanted to, but I think unless you have a monster-size ensemble, this is just noise. This is actually our first contribution to this problem in 2005. We were toiling in obscurity for a very long time before things got interesting. All right. I think I'm just about done, except to say that this works not just in this idealized low-order model, but we've done it for the community Earth system model. So this community Earth system model is the community model that is organized out of NCAR, the National Center for Atmospheric Research. It's the flagship Earth system model in the United States. And we see the same sorts of behavior for averaging these state variables over longer periods of time, and the ability to recover in an offline data assimilation approach. So Eugenio, here's another example where we don't want to cycle the CESM with a large ensemble for a long period of time. So we just do these RISDas by drawing from the CESM itself. What I'm showing you here is what happens if we only use 20-year data assimilation with essentially atmospheric and upper ocean variables. And I can't get into this measure of skill, but good is higher up on the ordinate, less skill down low. And if we use, say, monthly data, we can constrain the short time scales, not the long time scales. And if we do multi-scale data assimilation, and if we do both, we actually can get the benefit of both. And we actually get a little bit of a boost from the higher frequency information at these medium time scales. All right, so to bring it home, I hope the key points that I've made here, aside from the gross error that I made with the Lyapunov exponents, is that we have these practical solution methods. One is the variational approach, where we search through some descent algorithm for the minimum of some cost function that we can specify. We can also go through a direct solution, and those are Kalman filters. And the way we've kind of evolved through time to approximating these is with these ensemble techniques. And these provide practical estimates of the prior covariance, which in principle is huge, but in practice we can estimate with small ensembles. And the reason this works, the key message there, is that we have a lot of correlations throughout the state, and they vary in time. We can use a static covariance, but if we can use a dynamic one that comes from a model, we can get more information out of the measurements. And then the other bit here that I hinted at a few times early on with the scalar and then later on with the coupled climate problem is that functions of the observations may be more useful than the observations themselves. We don't often think about this with a weather problem because we have so many. We actually have too many. And the notion of thinning the measurement stream is actually perhaps more important. And part of that thinning could involve superobbing and averaging. But in other situations, like I showed you for the coupled climate problem, we may in fact want to consider functions of the measurements. And the key is boosting signal to noise for limited samples. It's really a practical problem. We're not pulling a rabbit out of a hat. At least I don't think we are. All right, so I think we're into the discussion section now.